In the previous sessions, we have seen the form of first law of thermodynamics for isothermal as well as adiabatic processes. In this video, we will see how the first law of thermodynamics is modified for isobaric process as well as isochoric process. So let us begin with the differential form of first law of thermodynamics. We write the differential change in the internal energy du equals an infinitesimal amount of work done, or I can start with infinitesimal amount of heat transferred d bar q plus infinitesimal amount of work done. That is the most general form of the first law of thermodynamics expressed for an infinitesimal process. Now, as we have taken hydrostatic systems as the example, this equation is further modified as d bar q minus p dv. So that is our equation to begin with. Now, for an isobaric process, pressure is a constant. Pressure P is equal to a constant. P equal to a constant. Hence, we have to rewrite equation number 1. We have to rewrite equation number 1 as such. There will not be any major difference in the equation number 1. I'll be rewriting equation number 1 in terms of d bar q. Let me rewrite equation number 1 in terms of d bar q. So what will be d bar q from equation number 1? The minus p dv term here will be taken to the other side. So it will be equal to simply du plus p dv. No other differences. Du plus p dv. So this is not a new equation where this p dv actually represents the work done. Okay, so let me write it other way also. D bar q will be equal to du, if I am considering this part of that equation, then to be du minus d bar w. That way also I can write. Okay, now let us interpret this equation. Let me call this equation as equation number 1. So you look at the figure on the right side. You can see the source here, the source of heat energy, a flame or a lamp. You can see it transfers an amount of q, or its infinitesimal amount is taken as d bar q. So d bar q amount of heat is given to the gas system here, and the pressure should be maintained a constant. That is our that is our need here. So you think of this way, how is it possible? When you give heat to the system, it will cause an increase in the internal energy of the system, or it will directly cause an increase in the temperature of the system. And the increased temperature means the molecules will be moving faster, and they may be making more collisions with the walls of the container. So what should happen to the pressure? The pressure also tends to change. Okay, So pressure also will tend to change if you just give some heat energy. So due to the rise in temperature, the molecular motion will become more frequent and will be making more collisions with the walls of the container, thereby increasing the pressure. But we have demanded that the pressure should remain constant. That is our demand. So how can that happen? That's the question. And the way in which you can keep it constant is that corresponding to the increasing pressure, you can balance it by increasing the volume. You increase the volume of the container. Okay, if you increase the volume available for the gas, then automatically what will happen? The pressure will get maintained. The pressure will be getting equilibrized. So in order to maintain the pressure a constant, the volume will be getting increased, and in increasing the volume, the system will be undergoing expansion, and when expansion is being done, you can say work is done by the system. And that is why in equation number 2 you can see a negative sign here. This negative sign implies that the work is done by the system. So we are trying to interpret the signs in the equations. Work is done by the system here. Okay. Now I can just interpret equation number 2 in this way. During isobaric process, pressure should be maintained a constant. So how is it possible? It's possible if and only if the heat that you are supplying to the system is utilized for two purposes. A part of the heat energy is used to increase the internal energy, and another part will be used up in doing work by the system. So for example, say that I'm giving some 100 joule of energy as heat. So let me say that this is the heat that is supplied. Let's say how this heat will be used. Suppose that out of this 100 joule of heat supplied, say that maybe some 70 joules, you say 70 joules has been used up for changing the internal energy, and the remaining 30 joule, by law of conservation of energy, the remaining 30 joule will be used for doing work by the system. So dW will be equal to 30 joule. So that is the application of the first law of thermodynamics for an isobaric process. So remember, for keeping the pressure a constant, the volume should increase, and a change in the volume is possible when the gas undergoes expansion or the work is done by the system. I can conclude in this way. During an isobaric process, the heat given to the system will be used for two purposes. One, for increasing the internal energy and hence the temperature of the system, and the other for doing external work by the system. Hope the idea is clear, and you can just see whether this equation is balanced, or whether the example I have given is in tune with the first law of thermodynamics given by equation number 1. Use proper sign conventions. So you will see that here if I am using du equal to, if I am using equation number 1, that is du equal to I am trying to give you some examples. Equation number 1, du equal to, let us see what is it equal to, d bar q. What is d bar q here in my example? That is 100 joules. I am writing 100, then say d bar q plus dw. plus dW. But here you can see that dW is the work done by the system. So as per our convention, dW should be taken as negative. Why it should be taken as negative? Because work done on the system should only be taken as positive as per our convention. So here I must take the work done by the system here as 30 as negative. So what is your final answer? You will be getting the answer as 70 units or 70 joules. And you can see this answer tallies with the sample that I have taken. So you can view the first law of thermodynamics either in terms of the change in internal energy of the system or in terms of what happens to the heat energy that you are supplied to the system. So that is about the isobaric process. Now let us come to the next case, that is an isochoric process, and it is quite simple matter. For isochoric process, the volume of the system should remain a constant. The volume of the system should remain a constant. Now, how can we maintain the volume of the system constant? See, it has been shown in the right side figure. I have taken the same system. You can see here there is a heat source which provides heat from outside through a diathermic bottom part of the cylinder, and you can see the piston has now been kept fixed by some stoppers fixed on both the sides. Some pins are used to keep the piston in place, fixed. So what is the meaning? Means I'm maintaining the volume as a constant. Volume equal to a constant. So this is what is happening now. So the volume is not permitted to change. Hence the piston's position has been fixed somewhere, right? And such a process is what is known as an isochoric process. Now you can clearly understand what will be happening. So for that, let's again go to the first law of thermodynamics, equation number 1. And since V is equal to a constant, automatically it gives you a result that the change in volume dV will be equal to 0. And we should be happy because equation number 1 gives you PdV equation, and where dV equal to 0, so this term PdV minus PdV term will be equal to 0. So therefore I can say equation number 1 will be modified as du equal to simply d bar q. Du equal to simply d bar q. And maybe you are surprised to see that on one side you have got what? An exact differential, on the other side you have got an inexact differential. See, don't worry about those things. The reason is that basically or physically both of them represent same type of quantity which is having dimensions of energy. Okay, so energy, the internal, the only meaning here you can understand. So you have to always make the interpretation this way. During an isochoric process, since the volume remains constant, the work done is equal to 0. Work done equal to 0, and hence you can see whatever heat energy that you are giving to the system will be used for changing the internal energy of the system. Or we can say or conclude that the heat is the flow of internal energy in an isochoric process. So that is our conclusion here. The entire heat energy, this is the thing to be kept in mind, the entire heat energy or heat transferred or gained, I can say the entire heat transferred or gained to the system, gained or transferred to the system is used up, is used for changing the internal energy, changing the internal energy of the system. of the system. So that is the conclusion in the case of isochoric process. Remember one thing, these conclusions will be useful to us when we discuss the topic of specific heat capacity. Let me give you a hint right here. Hope you remember the Mayer's relationship between the specific heat capacity Cp and Cv, and you wrote Cp minus Cv is equal to R. Cp minus Cv equal to R, where Cp and Cv are the molar heat capacity, specific heat capacity at constant pressure and constant volume respectively. So if Cp minus Cv equal to R is not meaning that Cp for a gas is always greater than Cv. Cp for a gas will be always greater than Cv. Okay. Now let me give you one more idea where we define C, the heat capacity, as something as dq by dt. So this is the basic definition of heat capacity, dq by dt. Okay. So to make it specific capacity, you have to divide it by the mass also. So if you want, you can write it 1 by M. So when you divide it by one mass of the system, it becomes specific quantity, already we have mentioned. So please think why Cp is always greater than Cv. The answer lies in the explanation of isobaric process condition and isochoric process condition. We will be revisiting this topic later, but this is food for your thought after the session. Okay, so we can go to session for the time being. Sorry for the disturbances that occurred during the session. Please pardon with me. Okay, thank you.